All right, today we're going to take a look at integers, and you're going to see some things coming about that you've seen before with whole numbers. Now, not everything is identical, but there are a good number of pieces that are just building upon what we already know. All right? The first thing I want to talk about is what integers are. The integers are your positive and your negative whole numbers, right? We've talked about them in that way before. So if you're sort of making a list of them like we have before, we usually start with a dot, dot, dot at the beginning and then a comma. And then we can list a few of the numbers in the middle and then towards the right-hand side, and we do that dot, dot, dot again. And this integers, your book must do this. Call them I. In other textbooks, they don't typically use I. They use Z here, just so you know if you were to ever see that in a book. Z is what's used for the integers. And the reason they do this because often textbooks will also use the I for irrational numbers instead, so there's this sort of a which one do I use it for question going on. Now, integer addition, we're going to look at a few models. We've done this before, right? Talked about models of how things look. So this is going to be a picture model for how integer addition looks. Now, the difference being that you notice I've got a positive 5 here and a negative 3. And that seems sort of unfortunate because how in the world do I represent a negative number in a picture? Are you guys following the problem here inherent in the way that this is even set up? Okay, so let me show you how we do such a thing. I'm going to do the one that you know how to do first. We're going to start talking about how we would represent the number 5, and we're going to do it with chips. That's probably big enough. All right, so you draw black symbols to represent 5 black chips, okay, 5 of positive chips. What happens next, however, is that you have 3 chips that you want to be in there, but they're supposed to be negative chips. So how do you do that? Well, what your book will do and what most will show to do is to make 3 chips, but those 3 chips are red. And the reason red is used is why? Can you guess? There's a financial reason people do it. People look at red as being a debt column. Microsoft Excel, if you've ever used Microsoft Excel, it does it. If you use it with formulas. If you add or subtract things, the default is that when it adds something or to subtract something and it's positive, it shows up in black, and if it's negative, it shows up in red. You'll hear businesses talk about this phrase of being in the black or in the red, and they're talking about whether they're making a profit or not. So I don't care so much whether you use specifically the red, but you want to use something else besides the color you're using, okay?
Just not shade it in.
You could not shade it in. That'll work too if you leave it sort of empty. If you want to use highlighters, you could use an orange or a yellow or something like that. In my own notes when I did it, I used purple because that's what I had apparently at the time with me. But something, whatever your standard color is that you're using to write with the pencil or the pen you're writing with, that's the black. Okay? Whatever else you're wanting to use, that's going to be your red. Everybody clear on what it's looking like so far? Okay, great. I'm going to use red because I have the ability to do it with the iPad, so I'm going to go with what your book's using and use that red. Here's what happens next, though. In this argument, what happens is when you have a black chip and a red chip and you combine them, they cancel each other out. Right? This is a positive number and a negative number. These two add up to 0. Those two add to 0, and these two add to 0. So there's a sort of a pairing relationship going on that we're pairing them up and we're removing them. Okay? So our final answer then has to represent the same picture, but only with what's left. So this is where we end up, and our final picture then has how many of what? 2 blacks in it. So the final answer is the number 2. Now, if the final answer had had red chips still involved, red and only red, then the answer would have been a negative whatever value it was. So this is a picture way of representing negative numbers. It's called the chip model. Everybody good with this one? There's another one that's almost identical. It has a little bit different feel to it, and you don't need colors to do it, so there's some good and some bad. What this one is it's a charged field model. You still have the same circle that you had before. Let's make it smaller. Still the same circle. But what you do instead of drawing chips for each number is you actually put in positives or negatives. So if we have a positive number 5, that means I have 5 positives in my diagram. And you can put them in there anywhere. There's no pattern or organization that you have to do, so make it as fun or as not fun as you want, I suppose. And then your 3 negatives are going to be represented with 3 negatives. And I'm only putting them in red just so that it draws your attention to the fact that they're there. There's not that you need to do them in red. Okay? And then just like on the last one, and a positive and a negative combine to become 0. So I pair them up and sort of remove them, if you will. And what's left then is that same circle I started with, and what's inside of it? 2 positives, which is the number 2. Everybody good with that? Now, do you agree that's the same thing as the last one? This is the same thing, okay? But it's a little bit different way of sort of thinking about it, especially if you have this sort of feel like, why should a red chip and a black chip disappear? Well, it's a little bit easier to argue with the one positive and the one negative, that those sort of, are balancing each other out a little bit. So it has a little bit different feel to it on talking about it. Number line example is a good one too. So with a number line example, we have a positive 5 here. So we'll start with whatever's at the beginning of the equation that we're working with. In this case, it's an expression. We've got a 5 here. So we're going to start with that 5. So what does that look like? Well, I'm starting with 0 on a number line, and I'm moving 5 in the positive direction. So here's 1, 2, 3, 4, and 5. So my value of 5 looks like this. This is a positive 5. And then I can talk about this negative 3 as moving backwards along the number line. So I'm turning around, I'm changing direction. So if I move backwards along the number line 3, again, I'm only using the colors just to draw your attention, not because you have to use colors. So if I move backwards 3 along the number line, so there's 3 units here that I've moved, where do I end up? What is the number of that location? The number on that location is 2. And you could use this very well to talk about things sort of in a picture sort of form of moving around somewhere. For instance, if I start out with Morgan and I count 5 desks in this direction, then I have 1, 2, 3, 4, 5, and I end up with Angela. And if I go 3 desks in the other direction, I'm 1, 2, 3. I'm back here in the room Kristen's in, and I'm 2 desks to the right of where Morgan was to begin with. So you can talk about that in a very concrete way and sort of moving around kind of thing. All right, there's also an idea of patterns. So some students really like patterns. Do any of you guys really like patterns? Morgan does, Angela does. I kind of like patterns. You kind of can see things. It almost starts to look like a game when you're looking at a pattern. I'm not very good at it all the time, but I find it challenging. It's an interesting thing to think about. So some people think like this. So let me talk about this in terms of patterns. So if you're looking at this in terms of patterns, I'm going to start randomly with adding 2 numbers together. And the 2 numbers are the original 5. That's not random. The positive 2 is a little bit random. Okay. So what is 5 plus 2? 7. No problem. We're going to add 1 less to the number 5 than we started out with. So what's 5 plus 1? 6. And we're going to decrease that one more time. What's 5 plus 0? 5. Well, we're just going to decrease that 0 one more time. So now I have 5 plus negative 1. And this is the first point now where I've got a negative number involved, right? But look at the pattern. After the equal signs, what's happening every time I decrease the number I'm adding to 5? What happens over here? It decreases by 1 as well. So I don't have to care or even know about the fact that what does this negative 1 mean. If I look at this pattern, I can see, well, it has to be 1 less than 5 because that's the pattern that's been going on up to this point. So this would then be the number 4, and then we can get down to, we're getting closer anyway, to the one that we want with the same thing. So 1 less than 4 would be 3. and then I add my 5 plus my negative 3, which is actually the one I'm supposed to be working on, and I get the number 2. So based on the pattern of what these are doing as I decrease that second value, that second term, I can actually see that my answer should be decreasing each time once as well. So this is a pattern sort of an argument. Okay, so those are the different models. There's another feature involved here with this, and that is the idea of absolute value. Because once we start talking about distance, absolute value becomes something that makes sense. I mean, I can talk about negative distance, but I don't really think about it that way, do we? I mean, we sort of say, yes, if it's 20 miles from here to from Shawnee to Oklahoma City, let's say Shawnee to Midwest City, that's closer. Shawnee to Midwest City, it's 20 miles. We would say also that it's 20 miles when you go back the other direction. We use the number negative 20 if we're talking about sort of a location maybe, but we don't really think of it in terms of negatives, right? We think about the absolute value of it. So let me talk about absolute value. And let me talk about the definition to start with. So the first thing is, if we have any integer x, and we talk about the absolute value of x, the absolute value of x has two definitions. The value is positive x, or the value is negative x. And I understand that looks weird, and I'm perfectly fine with that, and you will be too here in a minute, okay? So think about this with me. If you have a number like the number 5, what's the absolute value of the number 5? It's 5, right? Somebody somewhere along the way told you that if you have a positive number inside of absolute values, all you have to do is sort of remove those absolute value symbols, right? So the absolute value of 5 is 5. Okay, and in fact, that's what that first line says. The first line says if I have an absolute value of x, I can just take those symbols and I can just remove them. And that works when? When x is positive or? If it's not positive and it's not negative, it's 0. So this works when x is greater than or equal to 0. So write it for yourself if you want to see it written. We're talking positive numbers here and 0. If x is positive or 0 and we take an absolute value, we just take the absolute value symbols and we throw them away. Okay. I'm going to describe this a little bit more in a different way in just a second, but this is an analytical sort of a just symbols approach. The other one looks odd because this one looks like all of a sudden I'm introducing a negative, doesn't it? And I know that somebody along the way told you that absolute values always are positive, that the answer should always be positive. Well, the thing that I've not included on the first case was the case when the x values were negative, right? So this is exactly when this is happening. So if x is negative, then it's the second definition, and let me show you why. I'm going to use negative 3. So if I take the absolute value of negative 3, clearly I don't just remove the absolute values, right? Because you know the answer to this is supposed to be 3, don't you? Somewhere somebody along the way talked about this and they said, you throw away the negative and the absolute values or something like that, right? Well, let me show you what happens. Here, the x value, as we said, is actually the negative 3. And according to the definition, I should have the opposite of negative 3. What is the opposite of negative 3? It's actually positive 3. So the fact or the very reason why this negative is here is because it's taking whatever's inside of here and it's changing the sign. That's all this negative means. It doesn't mean the answer is going to be negative. It means the answer is going to have a sign change. If it was positive before, it would be negative. If it was negative before, it would be positive. However, we know that in this case, the x values are negative. It's the only time this works. All of this works based on a number line model, and I'll show you that next. So if we think about a number line, we can talk about this in this way. So if we're looking at a number x and it's on the positive side of the 0, then this distance is the value x. It's how much distance I've actually gone. Well, the problem is that if I go over here to the negative side, this value is also called x, but it's a negative number. So this is the number negative 3 or the number negative 7 or whatever it is. So this distance right here is still a distance, but it has to be that value with the opposite sign. So this is actually a negative x distance if this is my x value. Okay, again, it's the opposite of. That's what it means. So absolute value really talks about distance. That's what it does. And it's the way you've always thought about it, but the notation looks a little bit different maybe. Okay? So we're going to look at some examples that make us actually really think about what happens and when things are true and when they're false. So example number 5, we're going to classify each of these different problems as being either true or false. If it's false, we're going to show a counterexample. Do you guys remember what counterexample means? Do you remember, Angela? You want to tell me? Like, what does it mean to have a counterexample? If I ask or if I say I'm going to show a counterexample, what's it do?
An example where it shows that it's true or it's false.
Okay, well, so an example would be something that actually shows something's true. So we actually put a number in and it makes the statement, whatever it is, work. So a counterexample is an example that shows with new numbers or something that the actual value is false, that the opposite results. So when we're looking at this first one, part A, so we have to do two things, right? We first have to decide if it's true or false. And the second thing is if it's false, then we have to create this example. All right, so the first one here says we have the absolute value of x squared and it equals x squared. So is this true or false? It is true. Why in the world is this true? Okay. When do we get to take absolute values away, Carrie? Do you remember what we talked about on the previous slide?
When x is greater than 0.
Right, when we had positive numbers, or 0 itself. So when we had positive numbers, we were able to remove the absolute values and not have to think about this whole negative situation for sure. Why does that happen here?
Because when you square any number, it'll multiply it itself. So it has to be positive times
Right.
positive.
X squared, no matter what number you're working with, when you square it, it becomes positive. So I know for sure that what's inside of those absolute values is a positive number because it's squared. In fact, squaring isn't even the only thing that happens to make that work. We're going to get there in a second on the next one. So this is true because x squared is always positive. And I realize the directions don't actually tell us we have to write down the y, but I suspect if you look back at this later, you might not remember why. So I'm going to jot them down as we go. How about the second one? Absolute value of x cubed is equal to x cubed. It is false. Could it be true sometimes?
Yeah.
Yep. But if it's false, it means I can create an example where it's not going to work. Can you give me, what we want to do is we want to give an x value that makes this not work. Negative 2, negative 1, okay, yeah, either of those will work. I'm going to go with negative 2. Just because I don't want to lose the effect on the actual number itself, and that one sometimes does that. If I have the number negative 2, what is the value of negative 2 cubed? That is negative 8. Okay, so that's the left side of this equation. Sorry, I wrote this wrong. Give me a second here. Let me write it this way. There we go. That's the left-hand side of the equation, the side of the absolute values. On the right-hand side of the equation, I'm supposed to be doing that same value cubed without the absolute values. So what is the negative 2 cubed again? Negative 8. Okay. So far I've got a negative 8 on the inside of the absolute values, I've got a negative 8 on the outside of the absolute values. What is the absolute value of negative 8? It's 8. Does 8 equal negative 8? No. This doesn't work. 8 does not equal negative 8. So I filled the number in on both sides, and I showed that by doing so, the equation's not true. It's an equation that's not holding true. Does this make sense? That's what a counterexample does. It's an example that shows that this number doesn't work. It doesn't show that all numbers don't work, but it shows that this number doesn't work. All right, how about absolute value of x is non or not negative? Is that true or false? It is true. What did we say absolute values sort of have a natural extension to be talking about? Distances. And can we have negative distances for real? No, we don't talk about distance in that way. Same thing. Absolute values never give us negative numbers. Okay. Remember, this example right here doesn't give me a negative number either. It gives me the opposite of the value I had, which is a positive number in that scenario. Okay. How about part D? Is the absolute value of x always positive? So the answer is actually false, because the absolute value of x is either positive or 0. Namely, if x is equal to 0, then the absolute value of 0 is 0, which is not positive. It's not negative, though, right? That's why part C is true. It's not a negative number, but it's actually not a positive number either. So we can't go so far as to say it's always positive. Does this make sense? I know it feels a little bit like semantics at this point with some of these questions. That's what these questions are just going to feel like. You're going to have to really think. And sometimes it helps to think about concrete examples. Can I put a number in here and make this work? Can I put this number in and make this work? And as you're thinking, the numbers you should be thinking about putting in to make them work are numbers that are positive, negative, or 0. Okay? That's what's going to tell you whether or not something's true or false. Try plugging in numbers of 0. Try plugging in numbers that have negatives. Try plugging in numbers that have positives. If it's false, something's going to fall apart on one of those. Okay?
So why can't you plug 0 to part C too?
It would work because the absolute value of 0 is 0 and 0 is not negative.
Right.
Yeah, it's just, it's the language we use, right, to talk about it. And we sort of, in our minds, dismiss the case of 0 a lot of times. But it really has to count somewhere. So it certainly counts as being not negative, but it doesn't count as being positive. All right, the next set of things we're going to do is going to look like something you've done before. Properties of integers. You guys remember these? Yeah, we keep coming back to them, and they look the same every time, don't they? But if you'll remember, every time we do them, we sort of seem like we add something on, and we're going to do that again on these. Okay, so the first ones are going to be the same. The first 4 on this slide you have seen before. Closure property. What does closure mean? Somebody be bold and say it real. We did it with whole numbers. And what did we say with whole numbers?
It can only be like within that group.
Something like that. So the idea of it being closed is that if we take whatever group we're talking about. Right now we're going to talk about integers. Okay. So if we take whatever group we want to talk about, integers in this case, and we're working with the operation of addition, you saw, and we add 2 integers together, what's going to happen? We get another integer. So the closure property says that we set up here that we have integers a, b, and c. That if we take a plus b, we get another integer. And it's unique as well. Right? I can't add 2 plus 3 and get 5 today and 2 plus 3 and get 6 tomorrow. Okay, it is unique. But the real issue about being closed is this idea that when I do this, I still have the same kind of number I started with. So whole number plus whole number was whole number. And now integer plus integer is integer. Okay? Everybody good with that? All right. Second one, commutative property of addition of integers. What does commutative mean? What do you do? Let me write an example down. If I have a plus b, and I want to talk about the commutative property, what's the corresponding piece to this? B plus a. So the commutative property says I can change the order, in this case, of the addition, because I'm talking about addition. So we can switch the order around and it works. Associative is the first time that I start using what? 2 things. C and parentheses. All right, so I need all 3 letters, and I need to have some sort of a parentheses that indicates the order in which I'm going to do my operations. So if I add a plus b together first, because they're inside the parentheses, and then add c on later, what is that the equivalent to doing? Yes, so we'll do the a at the front just so that the order doesn't change. But the b plus c is the part that's in parentheses, right, Morgan? Yeah. So we're changing the location of the parentheses, but not the order of anything. The A, the B, the C, they're all the same order, but the location of the parentheses or the groupings change. And then the identity property of addition. Do you remember what the identity property of addition was before? 0. We have an identity element, some number that we can add to something and it doesn't change the value. So we have 0 is the additive identity. And we do have to say additive identity. Why? Because there's a multiplicative identity we talk about later, so we do need to say this is the additive identity. And it's true such that 0 plus A equals A plus 0, which is equal to A. So it has to work in both orders. Right? That was one of the problems that we ran into when we did this and tried to do it with subtraction, right? Is that if you do it in the opposite order, it all falls apart. But it doesn't all fall apart here. All right, there is one additional property, and then there's an additional theorem. So the additional property is the additive inverse property, and it says, for every integer A, we have a unique integer negative A, such that what happens when you add A plus negative A? You get back 0. And if we do it in the other order, it also works. Why didn't we have this before? We didn't have any negative numbers before, right? We had no identity or inverse elements before because we didn't have negations. We didn't have the ability to do this. Now that we do, we have inverse elements. And going right along with this, we'll do this one and then we'll stop, is that we have 3 different sort of properties that we use, and you'll use them all the time, although you probably won't even go back to think about it in this way. But let's just remind ourselves. What happens when we talk about the opposite of negative A?
They just cancel out.
So what does it become? A. So this is really, and I read it that way on purpose. The negative on the outside I read as the opposite of the value negative A. Well, what's the opposite of the value negative A? Well, it's positive A. Okay. The second one is if A equals B, then A plus C equals B plus C. And we had something like this similar before too. We use this all the time in algebra when you add equations, right? When you're working with simplifying equations. And then the third one is that if you talk about negative A plus negative B, you can talk about adding the values of A and B together and putting the negative on the outside of them. Sort of removing the negative from the discussion because they both have the same sign to be talking about anyway. All right.